Maybe if I do it here.
What about arrow keys?
Yeah, I think we go with arrow keys.
Yeah.
My experience with this thing is that when you bring something with high
Let's see if I
traffic,
can use
then,
my.
yeah, you can try your mouse.
Oh, you should be able to handle it the camera.
Yeah, on paper, but like I benchmark those things, and a lot of people complaining that.
See, I also have a laser pointer.
Does it work?
No.
Oh,
Does anything work?
yes.
That works. All right, I'll just let's do the old way. Okay. Okay. So, all right. Apologies for the delay. And thank you for having me. We're gonna talk about Markov categories. Maybe it's this way, which are maybe the best way to say it. To an audience of people that are familiar with Haskell, if lambda calculus is the internal language of Cartesian closed categories, then probabilistic programming is the language of what? And Markov categories are a potential answer to that. Okay. The surprising news is that just because of that, just because of the language, just because of pretty much the rules that we have there, you can do a surprising lot of probability theory without having to do measure theory. So in some sense, we can see Markov categories as being a very high-level programming language, and measure theory to be more like the machine code. So you can always compile things down, but you don't have to when things are particularly complex. All right, so I will give you a little overview of what Markov categories are and the main structures of probability with them, talk a little bit more in detail about how to do conditionals. We'll see the relationship with Markov categories and monads, and if there's time, I want to show you how to use them, in this case doing some statistics theory, like a little bit more in practice, and see how to do statistical experiments using Markov categories. All right, so let's get started, and of course, feel free to interrupt me at any point. The first idea of a Markov category is that it's a category where morphisms can be interpreted as having some sort of randomness in a very general sense. Okay, let's first start with the interesting examples. So maybe the simplest non-trivial example is K-star, the category of stochastic matrices. So imagine your objects are these sets like A and X, like big A and big X. The morphisms are these arrows which tells you like how to the morphisms are not these 5 arrows. This here is one morphism, okay? And it tells you like what's the probability of going from A to X, for example, and from A to Y, and so on. So you can organize these in a matrix, which is called a stochastic matrix, and has a property that the columns sum to 1. That's normalization of probability. And the entries of the matrix can be seen as conditional probability. You see this blue arrow, which is like this one here, is saying what is the probability of being in Z if we start in B, like a transition probability. Okay. So these one are categories. What does it mean? Well, we can compose them. So if there's a third set and arrows, for example, going here, what's the way of going from A all the way down to K? Well, there's 3 possibilities, through X, through Y, and through Z. You multiply this transition probability with this transition probability independently, as in a Markov process, and then sum over all the intermediate states, as, again, in Markov chains. And so that's the same thing as doing the row by column product of this matrix. And so this composition formula of probabilities is called the Chapman-Common parabola. So if you are familiar with Markov chains, it's exactly the same. Hence the name Markov categories. Now, before we get the wrong idea, I should also say, in Markov categories, you can also do non-Markov processes. They're just a little bit harder to write, but it's like the Markov case is the base case, that's the simplest case, and you can do everything. Okay. Let's also mention that you see the columns sum to 1. So the columns can be seen as probability measures. So you see, if you just consider the blue numbers, so index but just B, then that's the probability measure over X, where Y and Z have probability 1/2. So equivalently, matrices with just 1 columns, so matrices from the 1 point space, from the unit, those are the same thing as probability measures. So the states of your Markov category. All right. More interestingly, we can do everything in the non-discrete case, and we can do Markov kernels. So Markov kernel is like a stochastic matrix, but more complicated. So in general, you don't have map from what's the probability of going from X to some point Y. That's absolutely to 0. Look at what's the probability of going from X to a set here. So what's the probability of landing in this? And to make these work, then you want these assignments that, so to say, in the column entry it's measurable, and in the row entry it's probability measurable. Okay? Why measurable? Well, because as before we want to compose them, and now the sum becomes an integral. So we want the integral to make sense. Okay? So just a technical condition. But that's the thing. This what I wrote here, this integral, is just categorical composition. So we can just treat this as composition of morphisms, and you kind of don't see that it's an integral. You don't even have to wonder if it exists, because the way we construct this category is such that this always exists. Okay? Importantly, if we have an ordinary function from X to I measurable, then it defines a kernel which is deterministic. Like imagine this orange arrow is deterministic, so it lands exactly in a point. So it gives probability 1 to all the sets that contain that point, as 0 to the ones that don't contain that point. That's the way of forming a kernel which is not really probabilistic. So every non-probabilistic thing is a special case of a probabilistic success. And so we have a functor from measurable function to stochastic kernels. Okay? All right, so in general, what is a Markov category? So in the definition of a Markov category, there is no measure theory. One just proves that measure theory is an example of this, is semantics of this if you want. So a Markov category is a symmetric monolithic category, which we write as train diagrams, where we moreover can copy and discard information, as in each object has this canonical comonoid structure. So copy and discard satisfies some property. So these need to be a comonoid. So this kind of tells us that the interpretation as copying and discarding information is consistent. For example, if you copy and discard one copy, it's the same as doing nothing. Copying one copy or copying the other copy is the same, and copies are exchangeable. Then we have compatibility with a tensor product, technical condition. And then making more interestingly, we also have this that tells us that everything is coherent, as in, if I process some information and discard the result, that's the same thing as discarding the input to begin with for every process. This is related to the fact that probabilities are normalized, right? Because you see that if F wasn't terminating, then there is a difference between discarding the input and discarding the output after you've done it. So this is kind of a something that tells us that the probability mass is always 1. You can exclude this yellow condition. You get a copy discard category. It's not too different, but in this talk I will assume the yellow condition because it makes the math simpler. But it's not an essential difference. Yes, there's a question.
Sorry, my category theory a bit rusty. What is the difference between a symmetric modular category with copy and discard and the Cartesian category?
Yes, I hope to be able to answer that in one moment when I talk about determinism. But yes, that's a great question. But okay, so let's first say in Finstock, what is the copy map? Okay, so in Finstock, the idea is that from X to X times X, you can just copy the value of X and write it twice. So it's like embedding X into XX and Y into YL. Now, what I wrote here in blue is a function. So what's the kernel? What's the stochastic map? Well, X to XX has probability 1, and X to everything else is 0, and so on. Okay? For stock, so for kernels, again, it's something like mapping this to XX, which are the points of the diagonal. Again, what's the kernel induced by that? You have to test it on these rectangles, so these product spaces. So that's basically saying if X is in this rectangle is 1, otherwise 0. So that's the usual copying thing written as a kernel. Right? Okay, so let's, when we come to answer your question slowly, let's look at probabilistic concepts. What can we say using Markov categories? So first of all, we can say what it means to be random, or better, everything is potentially random. Let's see what it means to be non-random. So we call a morphism deterministic if it commutes with copying in this way. Okay, so what's the idea? If we process our x and copy the result, or if we copy our input and process the two copies separately, then the result is the same. That's determinism. Let's give an example. So in set, in the category of sets and function, everything is deterministic. Suppose you have x. Evaluate the function here. You get f of x. Copy the result. You get f of x, f of x. The other diagram, copy the input x on x and apply f to both. Then you get again f of x, f of x. So in every function behaves in this way. Now, I didn't use anything special about functions here. What I used is that set is a Cartesian monadic category. So to come to your question, actually every Cartesian monadic category is exactly a Markov category where everything is deterministic. But if in a Markov category everything is deterministic, then it's Cartesian. But not every Markov category is like that. Okay? So let's give an example where this doesn't happen. Suppose that our function is like this. Take an input, real numbers or floats, flip a coin. If it's heads, you add 2. And if it's tails, you add 3. So on the left, you see, we don't know if we get heads or tails, but we start with an input of 2. We may add 2 or 3. We don't know which one we get. Well, we know where we're going to add the same number to both copies. We do this before copy. These are correlated. So either we get 4, 4 or 5, 5. On the other hand, if we first copy our number 2 and then, flip 2 coins here, then everything can happen. Okay? In the first case, the coin will give us either 2 or 3, but then we copy whatever result we get. So these two things are random but equal, guaranteed to be equal. On the right, we're flipping the 2 coins independently, and so everything can happen. So in the first case, things are perfectly correlated. In the second case, things are actually perfectly independent in the inputs. Okay? So this is what makes our morphism stochastic. Like this copy stuff lets us detect the randomness of things. Whenever I give the talk to physicists, I usually misquote Einstein. Einstein is, sometimes people say, attribute this to Einstein, but it's not a real quote. That madness is doing the same thing twice and expecting different results. Einstein never said this. And I also don't think it's a good definition of madness. But it's an excellent definition of random. You do the same thing twice and expect different results. That's exactly this. Okay? So, one could view Markov categories as Cartesian monadic categories where one turns down randomness in a certain sense. This can be even made more precise using monads in a moment. Okay, so let's do some math now. In-stock and fin-stock. Let's do fin-stock so it's matrices. It's really easy to do the math. Let's solve this equation for f. So f and then copying y is the same thing as copying x and then applying f twice. Doing the math, that tells us exactly that f of xy, f of y given x, for every y and x, is equal to f of y given x. So is equal to its square. So the only solutions are 0 and 1. So this tells us that the only deterministic in this definition of stochastic matrices are exactly those that are exactly sure of where you're going. Like you know exactly what's going to happen. I'm not sure. So in the end, they are exactly the things that are not really probabilistic. Okay? And the same thing is true in stock. So this is actually how it was solved, sold to Markov categories when they showed them to me. Like this consideration of doing the same thing twice is a bit abstract. But once you put the numbers in, then you get exactly the deltas. You get exactly the things that are deterministic. So the probability is 0s and 1, and not like 1/2, 1/3. So this equation actually characterizes what it means to be deterministic. All right. So let's go forward. All right, the same thing for states. So a probability measure is deterministic even if it's 0 or 1. In probability, these things are called the 0-1 laws, or sometimes it's certainly independent of themselves. Okay, so another thing you can do with Markov categories is talk about independence. So we say that a certain distribution over x and y is making x and y independent, if and only if it is the tensor product of the marginals. Marginals mean just discard the other input. So this is the categorical way of writing what on the right here is written in the discrete case. In the continuous case, it's a bit more complicated than this. You have to take measurable stats and so on. But
Paolo, what is that triangle supposed to represent?
I'm sorry?
The triangle with the P in it. What was that meant to be?
Yes, the triangle is a morphism from the monoidal unit. It's classified in string diagrams, not the right I here. It's just nothing. So this way, times I is just X.
Okay, thank you.
So that's just, we can view the probability measure as a source. So it's like a channel independence on an input.
Yeah, no, sorry, makes sense now.
That's like something P of XY given. And okay, so this is, if this splits, then these are independent. One way to see this is something like, well, these things tend to be random usually, right? But if I know something about X, then I can know something about Y too. Like I have a bit less randomness of Y if I know X in general. But not if this thing split. If I can split them apart, then knowing X doesn't actually let me go all the way to Y in any meaningful way. Okay? And similarly, if there is some input, then we can talk about conditional independence. And so we can say that f, x, and y are conditionally independent given a if this is true. So that's the same thing as above, but for an input, but we see also it says the battery is weak.
Yeah.
Maybe we should plug this in.
Should be fine.
So why do we copy a here? Well, because you see in this equation on the right, we're using the value of a twice. The same a. It's not a prime. We're copying it. So it's really the same way as in this thing twice. Okay. Maybe I should ask. I don't know the background of the people. Actually, I also don't see most people here. Does everybody know what it means conditionally independent as opposed to independent? Or is that
People are saying yes.
all right, great.
But nobody's saying no, but not that many people are saying yes.
I'm saying yes.
All right. Okay, then let me skip the explanation of that. And let's go directly to the last probabilistic concept that we can study, which is almost surely. So usually in probability theory, lots of things are defined or unique or exist only up to a measure 0 set. And this is a major problem once you actually do the calculations. The good news is that we can do this categorically. The slightly bad news is that it's inevitable. So sometimes things really just exist almost surely. We cannot avoid that. But at least we can treat this categorically, and actually this notion is rather well behaved. So it's almost never in your way once you know how to deal with it. Here's a definition. We say that two channels, f and g from x to y, are almost surely equal. For some probability measure on x, you can consider this some statistics of the input, the prior, or something. If and only if these two things are equal. Let's turn this into numbers. So in Finstock, this is saying exactly that these f and g might be very different functions or kernels, but on the measures, they are the same. So that's the usual notion. And in Borel-Stock, it's also the same. Imagine a continuous measure here. You see, they might differ, but only on like isolated points of measures. So this diagram, once you do the math, is actually it's not a very complicated calculation to make. Corresponds to the usual notion of being equal, sure, or equal up to probability 0. Okay. All right. Let's now turn to conditioning. Maybe before I go, are there any questions? Seems not. Okay, let's get there. So, given a joint probability measure on x and y, a conditional distribution is a morphism from x to y that kind of reconstructs part of this joint. So remember that I said that when x and y are not independent, then knowing something about x tells you something about y. So this information flows this way from x to y in nice Markov categories becomes an actual morphism from x to y. Now, of course, knowing everything about x doesn't tell you everything about y in general, right? They're not perfectly correlated. So this flow here, this f, will still have some randomness, but that's fine. Because those are the morphisms of our category. So here's the condition such that the joint distribution can be reconstructed by taking the marginal, so discarding y, and then recovering the distribution of y by applying this condition. So that's the string diagram way of writing this. You know, joint distribution is marginal times condition. If you instantiate this for stock, then you get the usual condition using the integral. But again, this means exactly this string diagram. So in practice, when you work with Markov categories, you can just write that string diagram, use it, and not worry about the fact that it's an integral. The integral will exist and it will be that thing. It's not a problem. Okay, so
Paolo, I'm having sort of trouble reconciling what you're telling me with my knowledge of conditional probability, which is the Kolmogorov one, where you're projecting onto sigma algebras.
oh, sure. Yes, so here to reconstruct, so here we're in Borel stock, so all our probabilities, or all our measurable spaces are standard Borel. So in particular, the sigma algebras are constantly generated. So we can form kernels from conditional expectations. And now, if we want to do this with sigma algebra, what's going on is that we have as probability space x times y. That's the large probability space with measure. And then we are projecting down to x by discarding y.
Okay.
And so we're taking the sigma algebra generated by the projection onto x as sub-sigma algebra.
Okay.
So that's isomorphic to just x as a space in the category of kernels.
Yeah.
So the Markov kernel then from x back to y is the conditional, I guess the disintegration of that. Does that make sense?
Yes. So I'd like to see the details, but yes.
Okay, I can maybe talk a bit more about the details later. But yeah, so it is in Borel stock, it corresponds exactly to the Kolmogorov notions. All right, so a particularly convenient conditional is the Bayesian inverse. So suppose now that we don't have any joint distribution. We have one given by a source and the channel. It gives us statistics on the input and the output. This is particularly important statistic whenever you learn from data, right? You have, I don't know, you train a neural network, for example. You have the inputs and the outputs that you want in this form of distribution. Now we want to condition on y, for example, to find the optimal x. So this now instantiated the notion from the previous slide. It means finding some morphism which I write f dagger from y back to x, such that this holds. Okay. So in Finstock, this is the usual base formula, and in Borel stock is, well, the slightly more complicated ones, slightly more complicated formula, which means exactly the same. Okay. So again, this notion works in general, and again, it's blind to the fact that we're discrete, continuous, or even other things, but it recovers the usual notions of Bayesian inversion. Now, yes?
That is not something that exists in every Markov category, is it?
No, but we know rather well in which Markov categories it exists. So whenever we want to do Bayesian things, then we use those Markov categories. In particular, Borel stock
do you just
has that.
posit that it exists, or do you have a sufficient condition that is better?
We have a few sufficient conditions that are better. I'm now, together with a student of mine, trying to find the condition on the monad for which the Markov category has condition. So that would be extremely nice, but we're still working on that.
Okay.
We'll see. Okay, so whenever we have conditional, we can construct a category where Bayesian inverses play a major role. So let's do it in this way. So suppose we take a Markov category that has conditionals. Then this category we call prob stock of C. So something like a category of probability spaces and stochastic between them. So an object is a pair, which is an object and a state over that object. So for example, a measurable space and probability measures on it. That is a probability space. Okay? And as morphisms, we take morphisms that preserve this state, but only up to almost sure equality. Okay, so we're identifying any two things that are almost sure equal. As in, we kind of look only at where the mass goes as opposed to where the points go. Things that are, for example, outside the support of our measure are not considered, or things that are too small. This category is a dagger category, where the dagger is the Bayesian inversion. I'll explain in a moment what I mean by that. In particular, you can prove, again, just by doing string diagrams, that this category is equivalent to a category of coupling. So a category where your morphisms have joint distributions with your probability spaces, which kind of tells you where the mass goes. And what I mean is, if we have a morphism going from X to Y in this way, then we also have one going the other way, which is exactly this way. Now, this is really nice categorical properties, namely from the Dagger category. So I know that's not a very standard function, so let me give you a little primer on how this works. So maybe very roughly, a Dagger category is to a category as an undirected graph is to a directed graph. So in an undirected graph, you could have that, you see like here, A and B. Two things are connected by an edge, but they are not the same point. What it only means is that you can go from A to B, then you can also go from B back to A, but they're not the same. So in a Dagger category, it's kind of the same idea. So if you have a morphism from X to Y, then you also have one from Y to X. But that doesn't mean that they are isomorphic or that this morphism is an isomorphism. Okay, it just have this correspondence. And you still have identities and compositions, but these things do not have a preferred direction. So maybe the easiest way is relations. A relation between X and Y is like some pairs that are allowed and some that aren't, but does this go from X to Y or from Y to X? It kind of depends on how you look at it. But you can compose relations, and that's fine. And again, the composition is not particularly direct. Similarly, matrices are basically relations, except you have numbers instead of just this. Okay, and similarly, like graphs or weighted graphs also, if these are their just matrices, also are right, depending on how you look at them. So all these things are like these things that look kind of like matrices form a Dagger category. You can compose them. Matrices composed with matrix composition, but again, what are the inputs of the matrix, the rows or the columns? Depends on how you look at it. You can always take transform. So once you pick the direction, you stick with that, and you have a category. But otherwise, it's just this Dagger category. And now, what is the category of couplings? Well, it's pretty much the same thing, where you have joint distributions, which you can see as arranged as a matrix. This is a potential joint distribution of X and Y that projects down to this probability space or to this one. And so these are Dagger categories, and this one, this current, comes from this Markov categorical construction applied to start by taking these almost sure probability classes of morphisms. I'm not going to talk about it here. I can at the end if you ask me, but you can do a great deal of probability theory using this category curve. So, for example, very recently, with a colleague, we've proven a version of Markov convergence just using these categories. All right. So the general definition of a Dagger structure is basically an equivalence between C and C of, which is an actual functor. So in particular, if it's a functor, then the Dagger of the composition is the composition of the Dagger. So with Bayesian inverses, we do have this. So we can compose Bayesian inverses, and they respect the composition and the Dagger structure. Same thing with the monodal structure. All right. Any more questions here?
But this compositionality of the Bayesian inverse is only true if you quotient by almost surely equal, right?
Yes, and that's crucial. Yes, very much so. And that's the first place where it comes in. The other one is to actually have a Dagger, because Bayesian inverses are only defined up to measure 0. So if we quotient, then we have a Dagger. Otherwise, we don't. Yes, that's an excellent observation. Okay, let's look at monads now. All right, so what is a probability monad? Well, those of you that are familiar with monad Bayes in Haskell know that already. For those of you that aren't, it's a monad that intuitively equips your spaces with probability measures. So that do notation is basically probabilistic. The most famous example is the jury monad on measurable spaces. A simpler example is distribution monad on set. So you take a set, or if you want to type, and take px, which are like functions from x to numbers, so they sum to 1, so like discrete probability measures. The unit of the monad, so the return function, takes a point and just gives you that point with probability 1 and the rest with probability 0. So it's like how you encode the normal, the pure morphisms into that. And the multiplication, so this is how you write it in math. In Haskell, this is a join operation, so bind of the identity. What does it do? Well, it would take probabilities and probabilities and gives you just probabilities by mixing them. Let's see an example. So if I have a fair coin, and a coin that has 2 heads, so it's a coin that has probability 1 of being heads and 0 of being tails. So I have these 2 coins. One is fair and one has 2 heads. Both are in my pocket, and I extract one from my pocket at the probability 1/2 or 1/2. What's the overall probability of getting heads? I'm sure you've done it in your heads already. 3/4, 1/4, right? So what did I do? Well, mathematically, I took these averages of probabilities, or from the point of view of more like monads, I kind of removed these boxes. I unboxed these things. Okay, so mu removes these boxes and just from probabilities over probabilities give me just probability.
So it's the commutative monad?
This one is, yes.
Okay.
So if we have a Cartesian monadal category, so no randomness, and the commutative monad over it, which moreover is affine, as in preserves the monadal limit for normalization, then the Kleisli category is a Markov category. And yeah, it's monadal because it's commutative. So stock, for example, is exactly the Kleisli category of the jury monad. And Borel stock too. Thin stock is almost the Kleisli category of the distribution monad. It's a subcategory because thin stock has objects as finite sets, and P of a finite set is not finite. But you can find a very minor generalization that makes the statement. All right, so we have an adjunction. So what is a Kleisli morphism? A Kleisli morphism from A to B is the same thing as a morphism of the base category from A to PB. So, which we usually write as sharp and flat. So in Haskell, it's like this is how you write the normal code, and this is how you write it in the do notation. So this is an effect for morphism, which is probabilistic. So the one on the left and the one on the right are in bijection, so they encode the same information, but they are written slightly different. So on the left, we have a deterministic program. The program is deterministic. Takes an input and deterministically returns a probability distribution on B. As in, you are very sure of what the distribution is. On the right, in green, you have a probabilistic program. So this is not deterministic. It takes an input and returns a random output of B. Okay? So this, what's the difference between just having a probability distribution over B? Well, there's no difference. But the way for example, the computer will see this is actually different. Okay, so in particular, we can now sort of say apply the unit lemma. So look at the map, sampling map. So there is a map from Px to X, which is Kleisli, so which is the probabilistic, which in do notation is this, right? Which does what? Well, it takes a probability measure P on X, an element of Px, and takes a sample, takes one element, X, a sample from P according to this distribution. So it's the one that actually runs the tongue, pretty much, like the forces tongue, like that makes the probabilities actually happen. In basic probability theory is the stuff you write when you say, I don't know, I take a Bernoulli random variable with bias P. It's something that is 1 probability P and 0 probability 1 minus P. What's P? A number between 0 and 1, but those are exactly probabilities over the 2 elements. So that's the same. That's the same as the same in probabilistic programming. Like whenever you have, even in a program, even in a language like Python or something, whenever you sample from some distribution randomly, then this is the morphism that you're taking. All right, so a Markov category is called representable if it comes from a monad, and almost surely competitively representable if the bijection given by the Kleisli category is compatible with almost sure equality. So not only if things are equal here, they're equal here, but also if they're almost surely equal here, they're almost surely equal here. It's not always the case, but again, for the nice ones like Stock and things like it is the case. We recently proved that actually every Markov category satisfying a form of the Finetti theorem has this property. So basically all the ones for which you want to do some probability. All right, so why do we want these almost surely compatible representable Markov categories? Well, because convex combinations or mixtures are just categorical composition. Here's what I mean. I want to say that this, you see, bimodal distribution is a mixture of two Gaussians. Okay? It's like this Gaussian plus this Gaussian. It's a mixture model. How do I write this in Markov categories? Well, what does it mean 1/2 and 1/2? 1/2 and 1/2 is a fair coin. That's probability measure 2. So I say that P is the composition of a fair coin over a 2-element set, 1 and 2, indexing my probability measures. You see, Q1 is a probability measure, Q2 is a probability measure, Q of something is a Markov kernel. It takes 1 or 2 and gives you a probability measure. So it's a morphism of my category. So saying that P is this convex combination is the same thing as saying that P is this categorical composition. So this is how you do convex combinations using Markov categories. You just compose morphisms. Now, probability measures on X can be written as deterministic elements of Px or random elements, like in do notations this suggests. Probabilistic morphisms from X. Now, deterministic elements into Px, so we're one level of P up, or equivalently, random things into Px, we have to say they are mixtures of probability measure. For example, I say 1/3 of this, or 1/3 of this, or 1/3 of this, and mix them into this, either using the mu of the monad, as we said, or in do notation by sampling. What happens if we go even further up? Well, I want to say that if we go even further up, so the green morphisms to Px, we take partial evaluation of mixtures. What does it mean? Well, you see this thing down here is a mixture of these three Gaussians, but it's also a mixture of these two distributions. And I would like to say that this thing on the right is like more mixed than the one on the left, because you see these two things go into this one. Like some averaging there has already been done. There's been a partial evaluation. How do we do that? Well, with PPX. How? Well, what does it mean that we can partially mix this thing on the right? Well, it means that up there is the distribution over these distributions that says, okay, mix these two and take this mix with probability 2/3, so one level of boxes, and keep this. So you see now, mu, as we said before, just removes the boxes, and so just deletes these boxes, and we're back to like all these three things. On the other hand, P mu, so P here just means for each box apply mu, and basically means evaluate these mixtures for each box. So this box becomes this distribution, this box becomes this distribution. So a random element of PPX is a way of expressing this, this on the right as a partial evaluation of this on the left. This comes up in the theory of martingale, so I can tell a little bit more. Okay. So let's now go to the last part and put this into, well, application to statistics. So again, we take an almost surely compatible Markov categories, and let's talk a little bit about statistical experiments. What is a statistical experiment? Well, categorically, it's very simple. It's just a morphism, a channel. These are the parameters you want to find or estimate, and X is the things you can observe, and some prior over theta. Now, the definition is very simple, but of course, in general, this F is a very complex morph in practice. Now, here on the right is a very simple example. So a special case where F is deterministic. So in real life, it never is, but I'll do a deterministic ones because it's much easier to draw. Okay. So what does this do? This divides my space of parameter theta into 3 different cells and looks whether we land here, here, or here. Now, we can construct the posterior distribution, which in the language of Markov categories is going to be the dagger, so the Bayesian inverse, and then the star applying the monad What does that do? Okay, it has to go from x to theta. Well, okay, suppose that we have this distribution, right? If we land in x1, then we know that we are in the left cell. But where exactly in the left cell? Well, we don't know. There's still some probability, which is like a version of this slice of the red thing, but scaled up to 1. That's the Markov. And same thing if you're in the middle cell or in the other cell. So for each one of these, you get a normalized probability, 1 for each cell, which kind of tells you, what are these 10 like brown things? Those are the posterior distributions. If I observe x1, this is a deterministic experiment, so I know I'm in this cell, and this is my updated distribution. Now, in general, if f is not deterministic, things will spill a little bit over, like there's some noise, and also going back up, there's going to be some noise. But that's much, much, much harder to draw. So just imagine this with some more noise. Now, what do we notice? Well, we have this formula, right? Base formula, if you want. So what does this tell us? This tells us that this part of P is actually this rescaled normalized version, right? This brown one is normalized. Well, but times however high this thing was. What is this, like 1/4 or something? This total probability here is not 1. So this formula just tells us that these things are rescaled. So what does that mean? Well, that means that P, the whole thing, is actually a mixture, is a convex combination of all the 3 brown guys with coefficients given by the orange guys. Like this is just, this times this plus this times this and so on. All right. In general, of course, X does not have just 3 elements, and things are stochastic and so on. So this drawing is not a proof. How do we prove it? Well, using Markov categories. Actually, remember, mixtures are just categorical compositions, and just by applying the laws of Markov categories, you get that sampling applying to this is just this, and you're done. So there's like a 2-line proof just using string diagrams, and this, if you rule this measure theoretically, this involves like integrating over all the space and finding Bayesian inverses. 3 lines. That's the convex combination. It's an instance of what in measure theory is known as a showcase theorem. We can say more. Okay, why do we care about statistical experiments? Because we can compare them. So suppose we have 2 statistical experiments with the same prior. We say that P is more informative than, F is more informative than G. Well, if after doing F, you can reconstruct G by just experimenting a little bit more, like F corrupt your data a little bit more, and now you have G. Well, that means that G as an experiment is not as good as F, is it? What do we notice? Okay, so suppose we have F, again, with this reconstruction in these 2 cells. And suppose we do another experiment. Again, let me give a deterministic example, because it's easier to draw, but there could be noise. So you see now, for example, H puts a cell here, like puts together these 2 points and just keeps 1 separation. So of course, grains our things even more. All right, then, well, what is the standard measure? You see, from 2 points, we just split this into 2. Now, notice something. Split into 3, split into 2. So by what we said, we're tempted to say that the green is a partial evaluation of red, right? Partially to actually do this composition. It turns out this is the case, and is a theorem. So F is more informative than G, if and only if the standard measure is a partial mixture. The standard measure of G is a partial mixture of the one on F. Now, how do you prove this? Well, in one direction, it's just chasing this diagram. I'm not going to tell you the details, but it's just category theory. In the other one, in the other direction, you have to work a little bit more with string diagrams. There's some almost sure stuff. But the nice thing is that there's just a categorical proof doing this. And now, the discrete case for this was proven in 1955 by Blackmore. As far as I'm aware, the general case for non-discrete stuff never appeared in the literature until 1996, after more than 40 years. Even if conceptually, it's kind of the same thing. So why did it take so long? Well, because it's a, you can imagine how many integrals you have to write to make statements. How do we do this with Markov categories? You write a discrete case, you turn it into string diagrams if you can, and now it also works in Java. That's it. And that takes 0 years. Okay? So we still did it after 1996, right? I was 6 years old back then. But it still took us much less time. So I think this advocates for us, like at least for doing things like this, like generalizing from discrete experiment to continuous when the conceptual part is clear. Markov categories do give you like some really higher level. Okay, so I think I will stop here. Here are almost all the things that we have proven so far using Markov categories. Some we have reproven and sometimes generalized things in classical probabilities like the Finetti. We did information theory, statistics, some measure theory, and so on. So we want to get to the probability research level, and we're going there quite fast. So let me also mention some references if you want to know more. So I think the most introductory thing about Markov category that's out there is in this paper, Markov categories and entropy. It's a paper about entropy, but the introduction is, as far as I know, the easiest material on Markov categories to date. The stuff that I presented in this talk about experiments and statistics is in this paper. The dagger stuff is a little bit explained here too, in this third one. Bayesian inversions were first defined in this context by Bart Jacobs in this paper and Kentacho. There's additional work, not by me and not related to what I did, but still about Markov categories and Bayesian inverses in this paper by Di Lavora and Majorman, if you want to check. Last but not least, I said that the internal language of Markov categories is probabilistic programming. So these ideas are partly implemented in Haskell, in Lazy People. Some of you might know this. So if you want to check it out, here's the GitHub. Some of these features, including the lazy sampler, are now have now been ported into Monad Base. So if you're familiar with Monad Base, you might know some of this thing already. That's all I wanted to say. So thanks for having me.
I knew what I was doing. I'd clap my hands as well, but I'll clap them like that.
Okay,
Can I ask it? Can I ask about the? Sorry, go ahead.
No, you're after you, Joseph. Sorry.
Okay. I was going to ask about Finetti's theorem, because I guess you've told us what independence and mixtures are. What's exchangeability? What is that? Like?
Sure. Yeah. Exchangeability actually is so you have a group action on these sequences, right? Which means that they form a diagram in your category. So exchangeability is basically saying that it forms a cone in the sense of category theory, cone over the diagram of permutations. So a group is a one-object category. An action of the group is a functor from this one-object category. This forms a diagram. And so a cone over that, so something that commutes from permutations, is exactly an exchangeable Markov kernel. In particular, from the non-unit is exactly an exchangeable probability measure. And so the Finetti's theorem says that the space of probability measure is itself the limit of that diagram. So it's just saying that basically some limit exists and is given by the space of probability measures. Of course, Finetti didn't write it that way, because at that time, category theory didn't exist. But in Markov categories, you can make it a very nice categorical statement with a categorical proof. Like you can prove it just using string diagrams and moments.
I have a question as well.
Sure.
So you're linking probability theory in general to category theory, but there are many equivalent constructs in category theory. There are many equivalent approaches, and some are preferred and some are, they have different trade-offs. And so you're hinting quite heavily when you make the distinction between deterministic and stochastic errors, for instance. I mean, it sounds really much like function versus relations.
Yes.
Right. So and just like dagger category with rel, That's something that you find in relations as well. With distributor, that would be the equivalent of, the categorical equivalent would be distributor.
Yes.
Just like you go from function to relation, from functor to distributor. And so, and actually, one of your slides says, oh, when we get a monad and there are some conditions, then we get a Markov category. Yeah. So maybe the interesting concept is really those monads, and maybe there's some underlying more, I don't know, not more or less, but more abstract, from which we can generate easily some.
Yes, that's a really good observation. I agree. I suspect, but I have not worked in that. I suspect what's going on is that there's a story involving double categories. It's like profunctors, for example, form a double category, at least the weak version of, with like profunctors as horizontal arrows and functors as vertical ones. Same for relations. And Markov categories too, like you can form deterministic morphisms as horizontal arrows, generic morphisms, horizontal arrows, and deterministic ones, vertical. And the same thing also with the dagger one prop stuff. They do form double categories. I have never worked with them to see whether this adds some understanding. I really think it does. It feels like there should be something there, but yeah. So I still haven't completed. But I suspect that what you're saying is true, and the answer is probably in double categories.
So it's not a question, but just a funny realization, because we are pretty interested in neural logic and types that week. And not that long ago, we looked at something with Arnaud around differential linear logic.
Oh,
so the idea is that linear types gives you a way to say this argument is only consumed once, or like exactly once, but it's still the typing discipline. And sometimes you want to have this kind of the realizability version of the property is that without any types, you take any number term, and you want to see, is it linear? I mean, can you form some notion of linearity? And one answer from the people from differential linear logic is some kind of the dual of your thing, like it commutes with non-determinism, meaning that it doesn't copy, more or less. So it's funny to see that you do the reverse, you say something is random if it doesn't commute with copying. So
yes, so there is actually some connection with linear logic. I unfortunately don't know much about linear logic, but every time I talk about Markov categories to people that know linear logic, like
the internal language.
I didn't say anything. I protest.
Like, for example, there's this researcher up in Oxford, he studied here in Paris, and comes from linear logic, and every time I talk about Markov category, he finds some connection.
Yeah.
I don't know much about linear logic myself, so I don't know what's going on, but there is something with copying.
Yeah, and it's one of the set of linear logic is the internal language for symmetric modal categories, so there's definitely connection.
And then there's this comonad, right?
Yeah.
So, and I feel like, so here we have a monad on the base category, then we look at the Kleisli category. Then on the Kleisli category, the other side of the adjunction gives a comonad. So maybe that's where the connection starts. I don't know, though. Again, I'm the ignorant.
Yeah, so the comonad would give you the deterministic ones, I guess, if you could look at it that way, right? Which we've just cleared with linear logic, where the comonad gives you some, classical stuff or pure stuff in a way.
Deterministic for
Right,
Markov pairs. Yes, exactly. Yeah, so I guess it's something like that. So what we always get is a thumb force category, and so I guess the thunkable morphism is very often in Markov category, other exactly deterministic ones. So I guess the connection with linear logic is that you get the thunkable morphism from the comonad of linear logic, and then in nice cases those are the same thing as the deterministic ones. But like, for example, in Morales, it's probably goes up there. Any more questions?
guess this is it then. Does anyone want to say a closing word? Maybe I didn't shout loud enough. I will say goodbye.
Oh, yeah. Maybe they've gone.
Dominic, you have a question?
No, well, no, I've got lots of questions, but we're out of time, so, and I'm not sure how much interest there would be for other people. But
okay, well, feel free to send me an email or whatever you want. If you have questions.
I mean, I was just sort of thinking about, like the tower property of conditional probability. Presumably, that's a simple string diagram now, isn't it?
Yes, it is.
Yeah.
It is related to the fact that, see if I can go there rather fast. It is related to the fact that we have a dagger structure. So this category here, where we take Bayesian inverses, is dagger, and so it's such that the Bayesian inverse of the composite is the composite of the Bayesian inverses. So it's like it comes from here categorically in a sense.
Yeah.
So yeah, it is a categorical statement.
Yeah. I mean, it's a geometric statement with how I tend to think of it, but
Yeah,
I can see how you can do it with string diagrams now. Yeah.
It is a geometric, has a geometric interpretation, yes.
I have other questions, but more to do with Monad Bayes, really. But I can send you an email, Paolo. That's probably best, yeah.
Sounds good. Thank you.
There's also no harm in, you can stay on the chat as long as you want. I do have to run. So thanks for the talk, and I'll stop the recording, but I think the meeting stays open. So
yeah, I mean, I also have things I'm supposed to be doing before 6 o'clock. So 6 o'clock UK time. So I've got 2 hours.
Okay.